Hello, welcome to Noise Management and Control. This week we will continue our discussion on one dimensional waves, one dimensional acoustics waves which are propagating spherically. So, that is one part of the week, and in the subsequent part of the week we will start discussing about various technologies and issues related to noise measurement. So, today, which is the first day of this week, we will specifically talk about interference. So, the problem is, or the question which we will try to address today and maybe also tomorrow, is that if there are 2 point sources of sound and both these two sources are emitting some sound which is spherically symmetric. So, each source is emitting sound in all the directions and it is propagating uniformly in all the directions. So, let us call this as source S1 and this as S2. Then what we are interested in is that suppose there is a point far away from these two sources, let us call this point P. So, at this point we are interested in finding the sound pressure level. So, P, and that is a function of, so if the midpoint of these sources is this point and the distance between P and this midpoint is R and the angle with the horizontal axis is theta, then what we are interested in finding out is that what is the pressure at point P and how does it change when I change R or when I change theta or when I change time. So, once again the problem which we are trying to address is that if there are two sound sources, each of these sources are point sources of sound and they are producing spherically symmetric wave patterns, then how do these wave patterns add up at a far away distance point P, and that is the question at hand. And that is what is implied by interference. So, what could possibly happen is that, so first we will talk about some basic concept. Suppose the wave coming from source S1 is depicted by, let us say, this red curve. So, what am I plotting? I am plotting on the x axis time, and on the y axis I am plotting the nature of wave. So, from S1. So, this is the nature of wave coming from S1 at point P. Okay. Now, a possible situation could be that there could be another wave coming from S2, and because of the distance between S1 and S2 it may be arriving a little later, and if it just arrives just late enough so that when S1 is maximum S2 is at a minima and vice versa, then ultimately what will happen is that the total wave, the nature of the wave which was experienced at point P will be such that you add up these two and essentially you may get a flat horizontal line. So, you may not hear any sound at all. This is one possibility. Another possibility could be that when both these waves are in phase, then they will add up each other, and what you will hear is twice the pressure level, you know. So, the sound waves pressure level will become amplified, and it will be 2x if the magnitude or the amplitude of both the waves is same. And of course, there could be all sorts of intermediate possibilities where the waves are either more or less adding together or maybe they are trying to destroy each other. So, this phenomena is known as interference, and in today's lecture and probably also in tomorrow's lecture, this is what we will try to understand from the standpoint of physics. So, we know, so before we start discussing interference, we know that if there is a point source, if there is a point source and that emits sound in all the directions, uniformly in all the directions. Then the pressure of the wave at a point distance r is equal to real component of VVS divided by 4 pi r j omega rho naught exponent minus j omega r divided by c times E j omega t. So, what does this expression tell us? That if I have a point source, right, let us say we call this source S, and it is emitting sound in a spherical fashion, then if you have a point, let us say you have a microphone located here, and let us call this point M, and the distance between S and M is R. Then if I want to know what is the sound pressure level at location M, what is it? So, I can signify it as pressure at location R, so that is at point M and at time t. So, then the pressure can be expressed as real component of VVS. VVS is the volume velocity of the source, and VVS is a complex entity. It's a complex entity divided by 4 pi r times j omega. Omega is the angular frequency of the source. So, if it is just emitting one single frequency, then that is the value of omega times rho naught E minus j omega r times E j omega t. So, this expression we had developed in our earlier lectures. So, this is an important relation which we will use to figure out the total pressure for a problem like this, where we have two sources and we want to figure out the total pressure at point P, which is located at a distance r and at an angle theta away from the midpoint of sources S1 and S2. So, with this background, we will again reformulate the problem. So, let us say that there are 2 points S1 and S2. At point S1 there is the first source, and then the second source is labeled at S2, and what we are interested is in finding out the pressure at a far distant point, and let us call this point as capital P, and the pressure here is P, which varies with distance r, angle theta and t. The distance between P and S1 is R1, the distance between P and S2 is R2, and the distance between S1 and S2 is D. So, this is D over 2 and this is another D over 2, and this is the midpoint. So, from midpoint, if I draw a line connecting the midpoint to this far distant point P, then the angle between this line and the horizontal axis is theta. Now, for purposes of today's class, we will make some simplifying assumptions, but once you have learned this trick of how to solve this interference problem, you can use these this method to solve any problem related to interference, and it need not be require all the simplifying assumptions which I am going to state. So, what are the assumptions? So, let us write them down. So, the first assumption is that the volume velocity of source S1 and the volume velocity of source S2, they are same in magnitude. So, if volume velocity of source S1 is VV1 and its magnitude is this, then it is equal to volume velocity of 2, I mean the magnitude of second volume velocity, and let us call this parameter as, because it is common, VV. Okay. So, this is the first assumption. The second assumption is that the phase difference between the second source and the first source is phi. So, phase of V V minus phase of V V 1 is some number phi in radians. So, this is the second assumption, and the third assumption is that this distance r is very large compared to distance d, which is the distance between the two point sources. So, now we will start working on the problem. So, we can express V V 2 and V V 1 in terms of V V in such a way, in this way. So, V V 2 equals its magnitude times e to the power of j phi over 2, and V V 1, the volume velocity of the first source, is what? Its magnitude times exponent j times phi over 2 negative. So, if I write these relations, both of these relations tell us that the magnitude of first source and magnitude of second source is same, that is mod of V V, and the phase difference between these two sources is phi divided by 2 minus of phi over 2, which is phi radians. Okay. So, this is one thing. Now, let us look at pressure. So, pressure at capital point P, I am expressing it P as a function of r, theta and t, will have two components. One component will be due to source S1 and another component will be due to source S2. So, I will just write that in words. So, I will call it contribution due to S1 plus contribution due to S2. Okay. And we have already, we know how to calculate contribution due to S1 and S2 using the relation which I explained earlier. So, we will just use that relation to compute PRT. So, P r theta t is equal to real of exponent j omega t times V V 1 divided by 4 pi r 1 j omega rho naught E minus j omega r 1 divided by C. So, this is the contribution due to the first source, and plus the contribution due to the second source is exponent j omega t V V 2 divided by 4 pi r 2 j omega rho naught E minus j omega r 2 divided by C. Okay. So, these are the two contributions, and so this is the actual pressure PRT. If I want to find out complex pressure, so this is lowercase p is the actual pressure. If I want to find complex pressure, so complex pressure I express it as capital P r theta t, then all I have to do is I have to just erase it and and just replace small p by capital P, and here these real components go away. So, this is my complex pressure, and if I want to find the actual pressure, I just take the real value of it and I find the actual pressure at point P. So, that is not a problem. So, we will work on the complex pressure, and then later if we want, we can always get its real component and find out its actual pressure at point P. So, now we will process this equation further. What we will do is we will take j omega rho naught E j omega t out. So, j omega rho naught exponent j omega t divided by 4 pi, all this is common, into V V 1 divided by R1 E minus j omega R1 divided by C plus VV2 divided by R2 E minus j omega R2 by C. Okay. Now, we know that R, okay, so we have to find a relation between R1 and R. Okay. So, for this what I will do is I will go back to the picture which I had drawn earlier and let us look at this picture. So, this is R1, this is, no, I am sorry, this is R, this is R1 and this is R2. So, I have to find a relationship between R1 and R and R2 and R. To do that, what I will do is I will drop a perpendicular from here, from S1 on this line which connects the midpoint to point P. Okay. The other thing is we have to realize that this point P is very far from the sources S1 and S2, or in other terms we already have assumed that R is extremely large compared to D. R is extremely large compared to D. Now, this distance is how much? It is D over 2 sin theta. Okay. And if the if point P is extremely far away, very far away from the midpoint, in such a way that R is extremely large compared to D, then I can say that R1 equals R minus D over 2 sin theta. Okay. Why? Because these vectors R and R1, they will be almost parallel. The difference in distance will be just d by 2 sin theta. Similarly, I can also say that R2 equals R plus d over 2 sin theta. Okay. Now, if you run into a situation where this particular assumption is not true, then you have to actually use the actual value of R1 and R2. So, that depends on your geometry. So, since you know the geometry, you can always figure out the value of R1 and R2. But in this case, we are trying to make things simpler. So, we are making this simplifying assumption, but you do not have to do if you want to get a more exact solution. So, with this simplification, what we are going to do is we are going to replace R1 here and here and R2 here with R minus d over 2 sin theta and R plus d over 2 sin theta. So, that is it, that is what we are going to do next. So, I have j omega rho naught exponent j omega t divided by 4 pi VV1 divided by R1. So, it is R minus d over 2 sin theta, okay, exponent minus j omega over c R minus d over 2 sin theta plus VV2 over R plus d over 2 sin theta times exponent minus j omega over c R plus d over 2 sin theta, bracket closed. So, this is where we are. Now, what we are going to do is we are going to make this a little simple. So, we know that R is very large compared to d over 2, and the maximum value of sin theta can be 1. So, compared to R, d over 2 times sin theta will always be very small. So, I can drop this term out from the equation. Similarly, I can drop this term from the equation. Now, the question is, can I also drop this term and this term from the equation? And the answer to that is no, and the reason for that is, here I am comparing r with d over 2 sin theta. In the numerator, it is exponent j omega over c times r minus d over 2 sin theta. Okay. So, let us look at this term. What this term means is that it is a multiple of two terms. It is exponent minus j omega over c r times exponent plus j omega over c d sin theta. Okay. If this term was very small compared to this, I could have dropped this, but that is not the case, because what is e j omega r over c? It will be sine of omega r over c plus j times cosine of omega r over c. And what is e j omega over 2 c times d sin theta? It is again, there is a sine term and cosine term. So, both these terms involve one sine term and one cosine term, and there is no way I can make a successful argument that this sine term and cosine term is going to be extremely large compared to the other sine term and cosine term. So, I cannot make this simplification in the numerator. I cannot drop the d over 2 sin theta term in the numerator, but in the denominator, because I am directly adding r and d over 2, r and d over 2 sin theta, I can ignore its contribution. So, with this understanding, I make a simpler relation and I say that complex pressure P r theta t equals j omega rho naught exponent j omega t divided by 4 pi V v, and now because I have dropped r from here, so I can not r, d over 2 sin theta, I can take r out and I am left with on the inside e minus j omega over c r minus d by 2 sin theta, and this is V v 1 times V v 2 e j omega over c, excuse me, there should be negative sign here, r plus d over 2 sin theta. So, this is where we are today. What we will do tomorrow is we will continue this discussion and we will make this equation even simpler and then try to make some physical sense out of this particular equation. So, that concludes our lecture for today, and I look forward to seeing you once again tomorrow. Till then, have a great day. Bye.